Hi, this video will wrap up our coverage of the graph data structures. What we're going to do is a comparison between the adjacency matrix and the adjacency list. We'll see how they compare and why you might pick one over the other. Remember that an adjacency matrix is a n by n matrix of A booleans, so it's a big 2D array or vector, and an adjacency list is a vector of n lists of outgoing edges. Both are viable, they both work, they're both reasonably efficient and they do store a graph. The adjacency matrix has a faster has edge and remove operation, and the adjacency list has a faster constructor and out edges operation. So those are some differences. Here's this table that we've looked at a few times, and what I've done is highlight in yellow the significant differences between the two data structures. So the constructor or create operation is quadratic time on the adjacency matrix, linear time on the adjacency list, so the adjacency list is faster there. They're both tied at constant time for vertex count, edge count, and add edge, so we're not going to worry about those so much. The matrix has a faster remove edge, it's constant time, whereas it's big O of degree of I on the adjacency list. Has edge is also constant time versus big O of degree of I. And then adjacency matrix is slower on out edges. Adjacency matrix is linear time, but adjacency list is big O of degree of I. And then in edges, to get the list of incoming edges, it's big O of n times in the matrix, big O of n plus m time in the list. Those are two kinds of linear time. They're basically the same. There is a difference that matrix is proportional just to the number of vertices, whereas list, it's the number of vertices plus the number of edges. But in edges is a less frequently used operation, and they're both a kind of linear time, so we're not really going to focus on that distinction. Now, there's some other distinctions that are also kind of less important. Typically, in a typical use case of a graph, you construct one graph and then do many other operations on it. You build one graph and then add edges and do other operations to it. So the constructor efficiency is probably less important. Usually you make a graph, work with it, and then destroy it. You're not usually creating millions of graphs and never using them. That would be kind of weird. Also, typically you don't add a bunch of edges and then remove them. There aren't very many algorithms that are constantly adding and removing edges. So the remove edge operation is less important. There are some algorithms that need to remove edges, but they're kind of unusual or rare. So we're going to not focus on that in our analysis right now. So what remains after we kind of cross those off the list? Well, the adjacency matrix has the faster has edge operation. It's constant time in the matrix, but degree of I time in the adjacency list. However, the counterpoint is that the adjacency list has a faster out edges operation. It's big O of degree time on the adjacency list versus linear time on the matrix. So usually you'll choose which to use based on which of those two operations is the bottleneck in your application. Is it the has edge operation or the out edges operation? So here's how I would formulate the decision tree about which data structure to use. Is the has edge operation the bottleneck in your application? If the answer is yes, you should use the adjacency matrix because there's a very big performance difference between the list and the matrix on has edge. Adjacency matrix is constant time. It's much faster with has edge. But if the answer to that is no, in every other case, use the adjacency list. The reason is because the adjacency list operations are tied or better on all of the other frequently used operations. The adjacency list is also more compact in memory, so it's kind of a safer default choice. So that's the best practice I would advise. If has edge is your bottleneck, you should use the adjacency matrix, but in any other situation, your general purpose graph data structure is the adjacency list. So there are algorithms that do have a has edge bottleneck. They're the dynamic programming shortest path graph algorithms. So there's an algorithm called the Bellman-Ford algorithm. There's another one called the Floyd-Warshall algorithm. These are algorithms that compute paths and graphs, and they do this has edge operation a lot. That's the bottleneck. So for those algorithms, you should really use an adjacency matrix. But for pretty much all other general purpose graph applications, the adjacency list is a safe choice.